Howdy, folks. All right, today we are going to take a look at a little bit of hypothesis testing. Though most of that I'm assuming is a bit of a review on earlier stats courses, or the Stats 243 you may have taken already, or should have taken already as a prerequisite to the course. But we're going to touch on it a little bit and then move into the general linear model at the end, because we are, I guess, across most of the course so far, we are working towards linear regression, which will be the topic next week. So we are going to hit a little hypothesis testing and come to understand the general linear model, so that when we dive into that next week, we're ready to go. But in a very straightforward way, you're probably familiar with hypothesis testing in sort of base level science courses or junior high science level courses. You talk about hypotheses and generating the as part of the scientific method. When we talk about hypothesis testing in terms of statistical analysis, we're talking very particularly about a set or a suite of techniques, depending on your variable that you might use. But in all cases, there are some commonalities to them, and the most prominent is this idea of the null hypothesis. So the null hypothesis is it's kind of the Big Lebowski of hypotheses. It's the one that just says, hey man, there's nothing going on here, nothing to see here. In other words, you may be interested in a couple variables. Remember, our statistical analyses sort of begin with curiosity. What are we curious about? This is the point where you back off from being curious for a second and just say, well, there's probably no effect. There's probably nothing causing any sort of relationship between these two things. And it assumes, the null hypothesis assumes, or takes the stance, probably said better, that any sort of observable relationship between these two variables, or within a variable in its own variance, probably comes down to just normal statistical chance. So that becomes the thing we test. We test the idea that a given data set either lies within the realm of normalcy. In other words, often that alpha of 0.5 on a two-tailed test, or the 95% confidence interval, or if we fail the null hypothesis, if we reject the null hypothesis, we're saying, hey, that data set has a p-value or probability that lies outside, out onto these smaller likelihood tails, 2.5 on this side or 2.5 on this side. Our data set falls somewhere outside of that 95% range. And we're going to reject the null hypothesis and look into this further. But understand the null hypothesis, because it matters quite a bit that you do as we move forward. It quite simply says, this is, anything you see here can be explained by random chance. That there's nothing going on here outside the bounds of normalcy. And that's the thing we're going to actually test. So we seek to, through all of these methods, we seek to accept or reject the null hypothesis. If we accept the null hypothesis, we are, of course, saying, great, there's no effect going on here. If we reject the null hypothesis, what we are saying is, given our test, we're beyond the bounds of normal probability. In other words, we're outside of that 95%, and there's something to look into. And so the start of this process begins with stating your hypotheses, the null and alternative hypothesis. So the null hypothesis takes the stance of nothing to see here, nothing going on. And the alternative hypothesis is whatever your counter to that is. And your wording on those can be dependent upon what it is you're studying, or how you're approaching your statistic, whatever it is you're calculating. So we're not going to get too far into developing alternative hypotheses. In this case, we're going to keep it very simple as we move towards regression, again, thinking that this is likely a review of some other things you've had. There are some pretty well-established steps or stages in this process. So you state your hypotheses, you collect your data, you calculate your statistic, whichever of these it is, measures types of tests or analyses you're using. You construct your accept or reject region. In other words, you figure out what often that t distribution is. And then you accept or reject the null hypothesis. And that's the thing to understand, is that is what you're working towards. The goal of hypothesis testing is for you to say, I accept the null hypothesis, everything's fine, nothing to see here, nothing outside the realm of normal variation, or that you reject the null hypothesis and we should look further into whatever's going on here. So let's take just a quick look using a one sampled t-test and returning to our bowling balls and basketballs that we ordered up now several weeks ago. What's nice about this is we have a sample of these things that we hypothetically ordered up, and we have some weights and counts and measures. So let's bring those up here, hopefully, which I think can be done just like that. Okay, so we have our spreadsheet. These are just the data that have been brought forward from previously. So we have, in this case, we are on the bowling ball tab. We're looking at our 5 bowling balls. We've numbered them ordinally 1 through 5. We've given them an accession number. If you're doing artifacts or funnel assemblages or lithic assemblages, this would drop right in there. Which number artifact are you talking about? We know the size categories because we ordered these from, I forget the name that we gave the ordering site. Senditdirecttoyou.com gave us a 14-pound, a 16-pound, an 8-pound, a 12-pound, and a 10-pound bowling ball, and those were marked. We know which ball that is. We took a measure of the diameter in inches, since that's how they are controlled for, so they fit in the ball returns, and we took a measure of the weight, and we know what the weight size category was given the weight. We know what the actual measure was. So we can call that the control weight. We know what that size category was shooting for, 14 pounds, but the ball actually showed up at 13.6, given our measurement. So nice. We have a nice little data set here, and we have some information to work with. So how do we work through a bit of hypothesis testing? Well, what are we interested in? I think I'm interested in knowing if the sample of 5 bowling balls that we were sent is fits within the bounds of a normal or typical within the range of variance for a typical sample of bowling balls. I'm a little concerned that if I carry on with working with this data set, that I'm working with an abnormal amount of variance in a data set, and I just want to see that I'm not. If I am working with abnormal amount of variance in a data set, maybe I should get another sample or a larger sample. Both of those things would give me more and better information. In this case, I happen to have 5 bowling balls, so let's work with that. So we're going to set the null hypothesis. Of course, the null hypothesis is that this data set is normally varied. All right, the diameters of these bowling balls fit within the normal range of variation, and that the weight distribution of these bowling balls, again, away from their own individual weight of what they were supposed to be, also fits within the range of normal variance. That's kind of what we're interested in. Let's just make sure before we use this data set for the rest of the term that we're sitting in good shape. So in order to get there from here, you can see that we have we're doing a 1 sample t-test. So the most straightforward thing that we can do. And we have our formula for that here. Now in this formula are all the components that we've seen before. The sample mean, mu, or the population mean. In this case, it's handy because we know what they were shooting for. We know what all bowling balls in this size category, what their weight standard was out of the factory, if you will. So we're going to use that as our population mean. And we can, since we know each of these, we can just use the total. We have 1 of each, so we can just use the total mean of those as our mu, or as our population mean. And then we got to divide that by the standard error of the mean, which we took a look at last time. So we have our data, we have Excel opened up, we can just begin to work through this. Of course, you can do this by hand as well, but Excel makes some of this a little bit faster and easier. So we are interested in the mean of the diameter. Easy enough. We go for the average, and in this case, I'm just using the function pull down, and we highlight the area we're interested in, and that's the average of that. Now again, we can Control C to copy that cell, and when I move over here, it's gonna wholesale just copy over that exact same form of cells one line over. So when I hit Control C and then Control V as in Victor to paste, you can see that that drops the mean of the weights right in there. So it's cells D2 through D6, and this is the average of cells C2 through C6. Great. So we have calculated the mean of the diameter and the mean of the weight. Standard deviation of each of these is another thing we're going to need. So, oops, equal sign. We're going to get our function going. Standard deviation. And we're going to highlight the area or the range of cells that we want the standard deviation of. Again, you can go back and calculate this. You have all of that information. We are just now moving to shortcutting using Excel whenever we have already worked through a process. So there's our standard deviation. And to save myself some typing time, Control C, Control V. Congratulations to me. There we go. Now a function that you, well, at least we haven't used in this class is count. So n in this case is our sample size. Well, n is sample size. In this case, we know it's 5, but that's only convenient because we have a very small sample. If you have a large assemblage of artifacts or survey results, and you need to actually count the number of returns you've got on those, it may be completely impractical to do that by hand. There's a lot of things you can use, the simple of which is the function count. I use this one here, count if, quite a lot. It allows you to provide conditions for when they're counting. And I'll tell you that the time I use this the most in terms of teaching classes is to count the number of A's, count the number of B's, count the number of C's, etc. on exam results. So if I have a class of 200 people, I have 200 results and I want to know how many A's there are, but I haven't gone through and taken every exam result in a column where I see 90% score, A, 92, A, 88, B, so on and so forth. I just take the calculation for the percentage on the grades or the score on the exam. I do a count if, and I set the conditions for the if to 90 or above. And then I set the conditions for a B in the next one. I'll do a count if, and I'm going to count the B's, and I set that to 80 to 89%, so on and so forth. So anyway, count is the simplest one, and it is exactly what you would think by this point. We're interested in counting the number of cells in this range. And to absolutely no one's surprise, that should be 5. But we're going to Control Z and Control V it over there. And we have D2 to D6. Okay, again, it's really useful if you have a lot of data. It's a little bit silly at this point, but now you know how to use count. I recommend, if you're doing anything with Excel, look into count if and other types of count functions. They're very handy. Okay, we need the standard error of the mean. Now, standard error of the mean we calculated last time. Standard error of the mean is equal to the standard deviation and divided by the square root of the sample size. So that should give us standard error of the mean. Control C, Control V. We see that these are quite a bit different. As we're working our way through, you can pay attention to the stats. You see the means, you can see the standard deviation. So one is more spread and one is far less spread. The diameter is held pretty tightly, but there is far more variance across the weight, which we expect since we have different weight categories. Okay, degrees of freedom does equal, let's give you the equation, it equals n minus 1, or 4. So degrees of freedom is our sample minus 1. And now we have the population mean. So again, we're using sort of the standard, the industry standard to be our population mean, which assumes that as bowling balls are produced, they're going to drift around that ideal measure of, in the case of diameter, equals average of this set of cells. And it's going to be 8.5. But check it out. Control C, Control V as in Victor, gives us the average for F2 through F6, which is very handy. I could have done those here as well. I could have used the function thing. There's a lot of ways to get to where you want to be when you're doing these types of calculations. Find what you're happy with or works well for you. Okay, we're ready to think about something new moving into this because we have our bits and pieces at this point. So we need to calculate our t-statistic. And to calculate the t-statistic, we have it up over here. We need to take the average, or x bar, minus the sample average, minus mu, the population mean, and that is divided by the standard error, right there. So the population, or the sample average divided by mu, the population average, or sorry, the sample average minus mu, population average, divided by the standard error of the mean. That's what that formula is giving us. And we can see negative 0.315. Now, negative, what does that mean? Really, you could read this as plus or minus 0.3015, because what it's telling us is that's the point on that distribution, on that t-distribution, where our percentile falls. The negative is just telling you it's to the left of the mean. It's giving you the indicator to the left of the mean. It's mirrored on the right. So that's a little bit important because we want to use the positive value when we calculate our p-value next. But can we just copy this over? Yes, in fact, we can in this instance. And in this case, we can see that the average, or the mean of the sample at 12.04 is greater than the population mean. So that's going to give us that tail to the right. That's all that plus and minus are indicating for us. Okay, so now we're interested in seeing if the possibility, the p-value for this sample lies within the realm of possibility, and if it does, it will be greater than this value. And if it's a very out of whack sample, or very low likelihood that we would get a sample like this, then it will be smaller than. So let's see what we get here. To run the p-value, we need our function, and we're going to use t-dist, t-distribution. So what is it asking us for here? Well, it's asking us for our statistic. In this case, it's, or our value. In this case, it's the t-statistic. And instead of using or just clicking on that cell, I actually want to go with the positive so that I don't divide by a negative. So I'm going to use 0.3015, and I'm going to call that good. Divided by, or sorry, the next value we need is the degrees of freedom. There, I can just click on the cell. And the next thing it's asking for is tails. So it's a one-tailed t-test or it's a two-tailed t-test. We almost always use two-tailed t-test with an alpha of 0.05. So I'm going to put a 2 here for two-tailed t-test. If you put a 1, it'll just skew all that probability into the one-tailed t-test, which we looked at just very briefly last time. Let's see what we get. 0.7785. So we are well within the bounds of normalcy for that. Now, if I just take and copy and paste this over into this cell, it's going to carry over that incorrect t-statistic since I typed it in normally. So here, I'm again use our t-dist function, or t-distribution. In this case, we have a positive value, so I'm just going to click on it. And that's our statistic. We need the degrees of freedom, and we are running a two-tailed t-test. Wonderful. There we go. We are well within the bounds of probability given the weight. So for both diameter and weight with regard to our bowling balls, we're kind of all set on that front. Should we do the same thing with basketballs? Well, perhaps. I wonder, however, I haven't done this. Let's see just how well this works. Can we copy and paste the entirety of this over here and get something meaningful? Ooh, not quite, but close. We can move these up one, and then we have a little bit of figuring out what we have to do. So let's take a look. This is trying to tell us that the average is C4 down to C8. So those are off. That's not working all that great. We're probably better served to just run through all of that again. Now we could, if we had set up our spreadsheets between basketballs tab and the bowling balls sheet to be exactly the same locations, we could have copied and pasted those formulae straight over here, and they would have calculated correctly. And in fact, you know, if it took a little bit of time, we could actually do that. Let's see where this one comes in at. This one comes in at C9. So let's try that. C9. Let's paste those in there instead. Now that one gets an incorrect value. That one we know is going to be wrong, just using that. Now let's take these. Just move them up a bit. Let these go and see how close we come. C2 to C6. Yep. D2 to C6 looks good. We have a standard deviation of the same array. The numbers are calculating correctly. They're both 5. Our degrees of freedom are still good in terms of that. Our standard error of the mean, we have the mean being calculated at, we have the standard deviation here. That looks correct, and divided by the square root of n. So far, so good. Standard deviation divided by square root of n. Looks good. Degrees of freedom and population mean, E2 to E6. Yep. Population mean of weight, F2 to F6. So far, so good. Our t-statistic here is again calculating in the negative, on the negative side of the probability of the t-distribution, which is fine. We will just make our t-distribution read that t-statistic correctly. So it is 0.04278. We're going to cap it there. Okay, and that worked out pretty good. Now our t-distribution here is struggling a little bit because this is a negative, right? It is a negative and it does not want to divide by a negative. So instead of using that cell to inform our statistic in the t-distribution, we're going to go ahead and just give it the positive value on that distribution, which is 0.01, let's go 796. And there we go. It does calculate out. And both of these sit very, very comfortably well within, the p-value is well within the distribution. And in both cases for the size and the weight of basketballs and the size and the weight of bowling balls, in all 4 of those tests that we just ran, we accept the null hypothesis. By accepting the null hypothesis, we say that we have a perfectly good data set here, I guess is what we were testing in that instance. So, okay, we have done some little bit of one sample t-tests. We have done a little bit of hypothesis testing. And so I think we can bring it back in here and take a look at how all of this begins to work with a general linear model, because we're going to come back to hypothesis testing as we begin to work with regression on down the line. Before we do that, we need to talk about the general linear model. So what is it? Well, the general linear model, going back for a second, it doesn't explain why 2 things are related, but it does describe how, and it begins to describe it in a way that's predictive. So this is kind of cool, and we're going to work through it a little bit. The base equation for the general linear model is the equation for a line, which you should have run across at some point in your past, but in this case, y equals mx plus b. So to understand data in terms of a line, you need to know for any location of the x variable, where will y fall? So if something is a certain size, let's say elephants, and our model tells us that the bigger an elephant is, the more it weighs. So we're going to use elephant size, some sort of measure of size, we'll say length. Or interestingly, we could say length of trunk, length of elephant trunk is closely related to overall weight of the elephant. And that would be interesting. That's data we could record with regard to elephants. and we could put it on an X and a Y axis and say, well, elephant trunk length is closely related to or very predictive of elephant overall elephant weight. So what you're trying to do is to understand that if I know the length of the elephant's trunk, it will be a very good predictor of the elephant's overall weight of the entire critter. So it's the slope of a line and a y-intercept given x. I'll tell you where y is. So one thing to point out here is as we're working with this, we are still working with variance. So just because we know x, it is not a perfect predictor of y given a normal data set. The line is going to be best is understood as a best fit. It's the place amongst these data that's the closest to all of them, given all of them calculated together. But if you take a look, in other words, we have this point right here at about 3 of whatever variable this is, and it comes in on the y-axis at 6. But so does this one way over here at 7. Right? Keep in mind that we are still, in any given data point, can range and have variability to it. The line is a model that we use as a predictor. So that's what we want to focus on. So what is the general linear model? Well, it's a way that we can use to predict things or best fit the data that we have. Quick bit of defining here is your y-axis is location on the vertical side. M is the slope of your line. That's the one we're going to be trying to determine for the most part. X is location on the horizontal axis, and B in this linear model is the y-intercept. So in other words, where does that line cross the y-axis when x equals 0? Now, when you develop your variables and you develop your model and you develop your scale, you set your x-axis. That will, in a big way, determine your y-intercept. Because if you change your x-axis, it's going to hit the y at a different point. So all of this begins to matter quite a bit as you develop your variables and set this up. But let's take a look at an example. Now, for a couple reasons, we're going to use this. I would argue that you put this type of thinking, not this exact process, but this type of thinking into practice anytime you're going to bet on something. In this case, we're going to bet on Michael Jordan playing basketball against Challenger 1, Challenger 2, and Challenger 3. There's a couple reasons for this, but two primary ones. One, I just got done watching the In Their Own Words documentary series about Michael Jordan and the Bulls run to 6 straight titles. So it's kind of on my mind. We have basketballs and bowling balls as a main theme of the course. But most importantly, this commercial of Larry Bird and Michael Jordan playing a game of pig for a Big Mac is just one of the best commercials ever. And I was a huge Larry Bird fan. So I was always rooting for Larry. Often Michael won, though. What does that have to do with this? You have to bet $1,000 in each of these challenges. Michael Jordan is going to play Challenger 1, Michael Jordan is going to play Challenger 2, and Michael Jordan is going to play Challenger 3. You're going to put $1,000 on each of those games. So the stakes are enough for you to pay attention to, unless you're just running around with $1,000 that you don't care about willy-nilly. If so, that's fine. I'm not. I care very much about that $1,000, so I want to do a good job of trying to at least win 2 out of 3. That will net me $1,000, and I will at least feel like I didn't lose something. Ideally, I could win all 3, and that'd be great, but I want to hedge my bets as best I can correctly. So the goal is to guess who to bet on, Michael Jordan or Challenger, in each of these instances. And we do have a little bit of information. Fact, Michael Jordan is considered the greatest of all time. Okay, so debate that as you like, but he's pretty damn good. Let's just all agree on that. Fact, in the year 2020, which it is now, Michael Jordan is 57 years old. That's what Wikipedia tells me. It's fair enough. It doesn't matter too much, but we're going to go with it. We have specific challengers in mind, and we take a look at them. Challenger 1 is a little older at age 63, so 5-6 years older. Challenger 3 is quite a bit younger at age 35. And Challenger 2 is much older at age 75. So if I'm going to bet on these or just try to guess really quickly. Should I bet on Michael Jordan or Challenger 1? Challenger 1 is a little older than Mike. Probably want to bet on Mike. Challenger 2 is quite a bit younger than Mike at 35, but we are talking about Michael Jordan. And that one's a lot tougher. I'm not exactly sure which way I want to go. Or that's Challenger 3, sorry. Challenger 2, we can see is much older at age 75. I'm going to bet on Mike. I almost don't care who it is that's age 75. A 57-year-old Michael Jordan probably beats that person in basketball. But we actually produce models to do this, or at least we can, to get a little better idea to help us figure out about that Challenger, Challenger 2, or that's age 35. So we just set up an XY chart. We have the likelihood of Mike to win on the left from 0 to 100%, and we have age across the x-axis. Because we're going to take age to be our sort of major variable that we use to determine whether we think Mike's going to win or lose in each of these challenges. And also because age is what we're given. We don't know anything else about these challengers. We just know their age. So our x-axis here, we devised a scale that runs from age 20 to 90. So age 20 is our youngest age we're going to go with. It's about when most folks would be a challenger for Mike anyway, and we'll just go with that. We can do it a little younger. We could say age 18 if we want to say some sort of legal adult age or something like that. That would be fine. I just went with 20. It's a nice round number. All right, so where's Michael Jordan at? At any age, Michael Jordan versus Michael Jordan is 50-50 odds. So if you take Michael Jordan at any age or stage of his life and just copy and pasted him, and they played against each other, it should be a 50-50, it should be a toss-up. Just because Mike versus Mike at any age is 50-50. But what's nice about that assumption, we're going to make that as an assumption. Now, you see these assumptions a lot when you start working with linear models or modeling of any sort. You will make some sort of baseline assumption, and that might seem silly on the surface because we are talking about something that's you can't really do or seems completely obvious. But as we state it, we can see that it doesn't matter what age Mike is. We can put a pin in the idea that Michael Jordan versus Michael Jordan at any age is 50-50 odds. That gives us a starting point, because what's nice is now we can think, okay, Michael Jordan versus Michael Jordan is 50-50 at any age. But let's think for a second. What do we think the odds for Michael Jordan to beat any other 57-year-old might be? I have a number in mind. You put a number in your head. I think Michael Jordan is more likely to beat most other 57-year-olds. But I did just watch that documentary. That guy smokes a lot of cigars. And maybe that's, maybe his health is getting to him. I'm not sure. He didn't seem to be. I'm guessing he's still pretty darn good. But I'm going to say that Michael Jordan is at 75% to beat every other 57-year-old in the world. Doesn't matter who it is. He's 3/4 likely, or 75% likely to beat anyone. Now, this is really handy because it gives us a moment of M. It gives us a chance to understand where Y is given an X. In this instance, we know Mike is 57 years old, but we think he's capable of beating 75% of all other 57-year-olds out there. That gives us our slope at 1.315. With that, we can start to do things like this. Well, what about at what age does it become 50-50? You just work with that linear model. You work with y equals mx plus b. We'll get to the plus b in a second here. But we can work it the other way. Knowing the slope, we can say, well, hey, what is, let's solve for x when the likelihood is 50-50. And it turns out that given our slope, Mike is 50-50 to beat any 38-year-old in the world. So now we're working towards some useful information related to our bet. We had a 35-year-old on there, and we can see that Mike's 50-50 to beat anyone age 38 in the world. This is anybody, given the model that we're making anyway, or the information that we have and the information that we're working with, and a little bit of our own assumptions. Well, great. We can keep running this out in either direction. We can say, at what age is Mike basically 100% lock to beat anyone? Well, anyone age 76 or older, given our line and given some of our assumptions, we can pin MJ's 100% win rate at anyone 76 or older. Do I still feel good about this line? Yeah. Would I put it probably a little bit closer than that? Yeah, maybe it needs adjusted, but for now we're gonna leave it. We are just building a model. We are just trying to understand how some of these things might fall. But let's work it the other way and give ourselves a y-intercept. So we locked the scale of x at 20 to 90. It's fine. We could expand it. With this slope and the starting point, we can see that we arrive at a y-intercept of 26.3. If we had slid this down to 18-year-olds, it would approach something around 25%, give or take a little bit. And maybe that's a nice round number too. It's fine. But what we're really saying here in our model is that MJ has a 26% chance of beating anybody in the world, doesn't matter who it is. What do I think about that? Yep, I kind of like that. With the idea that anybody in the world, doesn't matter who you are, MJ's got a 1 in 4 chance of beating you. All the way down to every 20-year-old you might see, but it includes everybody else all the way across the line. So what we're really saying is MJ will never have less than 26.3% chance to win. That's the floor. That's as low as his percentage possibly goes. A 1 in 4 chance of beating everybody in the world, doesn't matter who it is. At least that, I would say. So what we've constructed here is what I think is a pretty conservative model. In other words, we could probably push this a little this way. And in fact, do I think MJ's probably got a little better than 26% chance of beating anybody? Yeah. Now I know there are other younger NBA players out there, and that's a pool of people who will perhaps have a likelihood of beating MJ right now fairly consistently. Probably not if you ask MJ, but certainly if you ask those younger NBA players, they would say, oh yeah, I could beat him. We could put those folks down here, but for most people, MJ probably beaten most 20-year-olds in the world anyway. But anyway, there we go. So let's take a look. Let's understand what we have. We're betting on Michael Jordan playing one-on-one against these 3 challengers. So if Mike's likelihood of winning is above 50%, we want to bet on Mike. If Mike's likelihood of winning is below 50%, we want to bet on the challenger. We already sort of written off challenger 3, who we knew was age 75. And given our model, that falls right here, or almost at 100% win rate for Mike. Still feel good about that. Challenger 1, we felt pretty good about betting on Mike because Challenger 1 was 63. But remember that Michael Jordan is 57 right now. This is only 5 years older. We don't know if Challenger 1 has just kept in outstanding shape. We don't know if Michael Jordan smoking cigars for most of his life has had some sort of negative health impact. We don't know if in recent years he's had some other medical issues. We start to understand that there are more variables here that could matter than there were up here. And our line is reflecting that a little bit. Now, the one that we had the most wondering about is we are talking about Michael Jordan, and we are talking about someone who's quite a bit younger at age 35. In fact, at age 35, someone's sitting sort of right in that prime, if you will, of their sort of physical capacities. Some people would argue, well, that's actually closer to down here. In terms of basketball, where physical ability meets skill, if you've been practicing and playing basketball the entire way along, you do come to a point sort of in the late 20s to mid 30s where your skill and your athletic ability do sort of peak. They come together in a line. Okay, because after that point, physical, your physical abilities will go down a little bit. Even as your basketball skills improve, this total sum can or is modeled to become less. Either way, that challenger 2 at age 35, given our model, is on the bet against Mike side. So we look at our model, we bet on Mike against challenger 3, we bet on Mike for challenger 1, and we bet against Mike for challenger 2, and see how it goes. Now, that fits pretty good. Some of the problems with this: we were only working with a variable of age. As we think about it, or as we work through our model, some of this came up. What other variables would inform our decision? Well, it matters perhaps very much who those people are, not just their age. If it's me, you should bet on Michael Jordan 100% of the time. Michael Jordan is going to beat me in every game of basketball we were to ever play. I just guarantee it. It's just never that good at basketball. But if it's someone like Larry Bird, maybe that changes. So what other variables could inform this? Well, the skill level of the players involved could be a variable that matters a lot more than the age of the players involved, potentially. So when we start talking about that, we start talking about how much we can weight or understand the closeness of fit of those variables. In this case, age probably has quite a bit of variation in it, given the entire human population, because we don't know the skill level of the player involved. If we know the skill level of the player involved, but don't know their age, that perhaps gives us a tighter model or ability to more closely model who we should bet on. So in other words, if we had some sort of measure of skill, however you want to imagine that we would measure that across our x-axis, we could probably more closely define who we wanted to bet on, because it would take some of the variance out of that data set. Here's what that would look like. So our players were actually Michael Jordan versus Danny DeVito at age 75, versus Larry Bird at age 63, and versus LeBron James at age 35. Now that information adds another variable into the mix, but you immediately can see that it's probably a more important one than age. So we would say that there's a pretty weak correlation between age and MJ's skill at beating the entirety of the human population. Or in other words, someone who's a professional basketball player, that variable alone is more important than just age. The solution to trying to figure this out or form a more better model is our hypothesis testing and linear regression that we're going to get into next time. But this type of model forming through fitting a line to data is at the heart of the linear regression and trying to understand or describe data sets that we're going to work with for the rest of the time. For the meantime, let's take a quick look. We have our model and we have our 3 challengers here. At age 75, we now know Danny DeVito. Danny DeVito versus Michael Jordan at any age is like 100% Michael Jordan I'm going to bet on. Now, Larry Bird's a little more interesting. Our model put him up here at like about this 75 to 80 kind of percent win rate. But now that we know it's Larry Bird, who is the 63-year-old challenger, Larry Bird isn't just a professional basketball player. He was a top-tier professional basketball player, but he is a little older. But we can see that Bird's a little more likely to win against Michael Jordan than just average Joe 63-year-old person. And so our actual data point is a little bit closer to that 50-50 line. Our 35-year-old challenger was LeBron James. LeBron James currently sits at sort of the peak of his career. Where would we put LeBron James's chances right now against a 57-year-old cigar-smoking Michael Jordan? Probably a little better than what our model predicted. So Michael Jordan's likelihood of winning against LeBron James is perhaps a little lower than what our model said. So we did bet on this challenger. So we were probably more secure in that than we thought. But we can see with the 63-year-old, now knowing it's Larry Bird, we were a little less sure of what that could have been. But when we take into account, so we have those 3 data points, but let's take a look at the entirety of the human population, or at least a mock-up of what I think that would be. a little more like this. So this isn't the entire 7 billion people on the planet, of course, but by age, we likely have a couple very highly skilled NBA players who are younger than Michael Jordan, who fall on the side of better than the model predicts. Again, this isn't better than 50-50. This is better than the model predicts. This is the LeBron James as compared to general 35-year-old person. LeBron James being a high-level NBA player has a better chance of winning than just, let's say, normal 35-year-old person off the street. That's what that's showing. But as you take a look at this, it becomes pretty obvious pretty quickly that the majority of the human population is way up here. So we've made this model, but we can, once we have some data, we can see that this linear model, while it was useful given our task, does not well fit this data. In fact, it's probably something like Michael Jordan's percentage to win rate against the human population is likely quite high. And we can see if this is our actual data distribution. It could be something like this, something up here. Is the actual line? Well, linear regression, when we get into next in the next lesson, is going to be how do we generate a line that's a best fit given the data that we have actually collected. And so we are going to go with that for next time.